So good morning. I will try to give my presentation in, let's say, 15, 20 minutes, and then we keep some few minutes for questions. As you can see from the title, today I will present a few of our work on novel feed spacers for membrane fouling control and flux enhancement. This work, of course, I'm putting my co-workers from KAUST, but also we did this work in collaboration with the University of Technology Sydney, where Professor Sean team in Australia. So as you know, feed spacers are very important. So I will talk about the relevance of feed spacers in water filtration in general. And then the impact of the spacers for the performance in general, the overall performance of membrane processes. And then our design, which is based on symmetric spacers and how the performance is improved. And I will support this with experimental data and some simulation using direct numerical simulations, so DNS. And then I will draw a few conclusions. So you all know that spacers are used in the spiral wound membranes, reverse osmosis or nanofiltration, and even ultrafiltration. And spacers are also used in plate and frame, discs, whatever, because in general, the spacer for the spiral wound, as an example, is a support between two membrane sheets. Otherwise, the water will not flow between two membrane sheets. But more importantly, it also generates turbulence and unsteadiness inside the flow channel that enhance the mass transfer and reduce the concentration polarization and therefore increases the permeate flux. On the other hand, these spacers are creating some problems, and one of those problems is the increase of pressure drop and fouling promotion. The increase of pressure drop is due to the obstruction of the flow going on because we are putting material in between the sheets. And the promotion of fouling, I will come in a moment in the next slide. So in general, the geometry parameters or geometrical parameters of feed spacers are based on spacer orientation, because you have a spacer and then orientation, the mesh length, which you can see here, LM, the internal angle of between the two filaments, the diameter and shape of the filaments, shape and diameter, and the porosity of the channel, because we are putting material. This is based mostly of plastic based, and we are putting material, so the less material, the best. And these dimensions of feed spacers affect the hydrodynamics of the fouling growth inside the feed channel, as you can imagine. So how the feed spacers promote fouling? So it has been demonstrated a long time, like in the early to maybe last decade, that these spacers are actually the cause of membrane of the fouling attachment, and especially biofouling. So you can see here simulation dynamics and some experimental data. The attachment of fouling started actually on the filaments and in the corners here, as you can see in the intersection of the filaments. And this is another schematic showing this is the flow direction, and that filaments, the intersection filaments, are actually obstructing the flow, which is very obvious if you see the hydrodynamics point of view, which makes a lot of dead zones. So dead zones means the velocity is different from a membrane place to another one. That is one of the biggest challenges. So a lot of experimental data followed these works and showed that actually the spacer was full of biofouling or even organic attachment. So commercial spacers designs, I'm using here, this is the real one. And in our work, of course, we printed this, even the commercial one, we take the CAD and we printed it. The reason for that is just to have the same way of our novel spacers, so that our comparison is very fair. So the commercial spacers are like this. This is the 3D printed, which is exactly similar to the commercial one. And you can see here the hydrodynamics of the feed spacers using DNS. And I compare it with our spacers, symmetric spacer, which is here. This is the 3D printed one, so SEM image. And you see here, I have a small animation showing the unsteadiness representation of the flow, which is quite more distributed than the commercial spacer. This is the first point to highlight. So we use the CAD to fabricate the spacers ourselves with using advanced 3D printing technology. So what are the spacers? I will just give you some of the spacers developed by our group. The one is, maybe you heard about it, which is the perforated feed spacer. I remember when I showed you that the foul lengths are mostly on the intersection. So the first idea came to make a hole in the intersection, and we call it perforated or hole type spacer. And you can find details of this in these publications. The perforations, we also try to have more, not only in the intersection, but also in the filaments. So one hole or two holes or three holes, whatever we could make in the filaments to see how much turbulence we can generate and is it good or not. And believe me, it's not always good to have very high turbulence because this also generates more fouling. Another spacer is the column spacer. So we can, because the spacer is sitting on the membrane, and you might have some maybe reduction of the membrane surface maybe or something like that. So we reduce that by putting pillars in the intersections, and the filaments are actually in the middle. So you have like a void in between. This we call it column type spacer. Then we had another spacer, which we call it dynamic or turbo spacer. Actually, the first time Professor Sean was explaining this using these helices turning around. I mean, it's like real when you have the flow, of course, by the flow. It's quite challenging to print them, but you know the results were really outstanding. Maybe one of the issues of this spacer is the scale up or how to make it in a spiral one. But keep in mind, this turbo, whatever these helices are very small, really a millimeter big. So it's possible to scale up. And we also reported another type of spacers, which is twisted or helical type spacer. And you can find details of these spacers in the literature. I put here papers. So let's give a few examples of these ones. So regarding the perforated spacer, as you know, the spacer, a lot of developments of novel spacers, mostly based on spacer orientation and internal angle. People are changing the angle, like a 90 degree, whatever, 45, 62, etc. To improve the hydrodynamics and to reduce the fouling, as explained before. However, the perforated spacer, or the hypothesis behind the perforated spacers, is beyond that. It's first, the creation of these holes will increase the turbulence. How they increase turbulence? We believe that at the exit of these holes, you will have like micro jets, like a jet, to push or to flush away all the foulants deposited here. Of course, the foulants before the hole will be driven and will go inside, and will reduce the dead zones because the dead zones are mostly behind the intersection of these filaments because there is no turbulence. Then we suppose also that we are reducing the porosity because we are using the same spacer, but we put a hole, means we removed some material. That means we have higher porosity, and this will help in reducing energy and, of course, so many other things. So, of course, we built our own experimental setup with three in parallel to have the same comparison. We want to have a fair comparison between the spacers, so everything was in the same, under the same conditions. And we use OCT, optical coherence tomography, to look at specific places, including the spacer or the membrane, and to see what's going on the membrane and how we could, and everything, of course, is logged in using data processing in the computer. Okay, so regarding the, if we see the flow dynamics at elemental level, when we take one element, which is one cell of the spacer, This is the hole type. I'm giving directly here the OCT images because I have already presented this specific case earlier. You can see here that, you know, the spacer without hole, after 60 hours or 40 hours of filtration, we see clearly the a big or large fouling layer on the membrane surface, which is called the fouling thickness. And of course, we could even measure the fouling layer, like here, 160 micrometer. And of course, we followed the build up of this layer from 1 to 2, 3, 4, how this layer was built up. Sometimes there is some flow back, etc. So this is like at a specific 40 hours. But importantly, that with hole spacer, there is no fouling layer on the membrane surface. It's like flushing away all the foulants because of the turbulence. And I will show you some simulation data which confirmed this result. And you can see here this section of this, as you can see, the hole actually made a lot of turbulence nearby the intersections and reducing the dead zones. If we see the simulation at the elemental level, you can see this is the typical spacer, and the dead zones are, as I explained before here, and this is the flow hydrodynamics. When we increase at the turbulent state, this is steady state. At turbulent state, you have much better dynamics, but still we have a lot of dead zones, especially at the intersection and maybe near the filaments. But once you have the hole, you know, we flushed and most of the dead zones are almost disappearing. So this intersection actually enhanced the flow velocity, as you can see here, and the recirculation vortex have been created, enabling the fouling deposition and, of course, eliminating the dead zones. This is at the DNS of multiple cells, because most, if you are doing this kind of work, I suggest you to don't do only one cell, you have to do more, 3 or 4, because the situation is completely different. So you can see clearly here the microjets created here, but you can see what's in red on the filaments. This is the deposited foulants on the membrane surface. So I will share with you this presentation because of time. I will move on another type of filament, but this is just to show you the creation of these microjets, which enhanced the flow dynamics and reduced or the detachment of the foulants with the better mixing, of course. The other one is, now we want to take this advantage of the hole, but by using the pillar, because we as I showed you before, we had some work with the pillar, but without hole, and it showed much better performance than a commercial spacer. So why not combining both, the pillar with the hole, and only one hole at the intersection, as you can see here. And these are, of course, the 3D printing spacers. So the data is really promising also. Now we did these experiments for 67 hours. And you can see here the data. This is the commercial spacer, the pillar, and hole pillar. So we used all of them to see. And what you see in blue is the average permeate flux. The green one is the specific flux per bar, every 1 bar, because we use different pressure, as you can see here, just to have a good comparison. And the red one is the flux or specific flux enhancement compared to, relative to the commercial spacer. So as you can see, the hole pillar has the highest and 75% enhancement compared to the commercial spacer. And at higher pressure, we still have the highest performance, but lower percentage. So very high pressure is not, as I told you before, it's also creating maybe more fouling than low pressure. And this is for ultrafiltration process. So we are using these spacers for different processes, forward osmosis, reverse osmosis. So today I'm presenting for the ultrafiltration because it's simpler. The DNS also showed a very good performance, as you can see, exactly what has been shown in the experimental. As you can see here, the dark violet color indicates the flow separation area, which is the dead zones created by the commercial spacer. And you see this negative x, which is this direction velocity magnitude, and the comparison with a pillar spacer, and this is pillar with hole spacer. So you can see here the microjets at the exit of the intersection. It's visible behind these pillars, and it's effectively enhancing the flow hydrodynamics and minimizing the dead zones, and of course enhancing significantly the flux performance and reducing the pressure drop. So the pressure drop has been significantly reduced by 15% or more, and the flux, as I showed you before, enhanced by 75%. And if at higher pressure, it was less, but still very high performance enhancement, like 65% for 1 bar, 55% for 2 bar. So the OCT images of this also, as you can see here, again, I always make the commercial spacer in the left side here, then the pillar spacer, and then the hole or the pillar with a hole spacer, as you can see in this image. And you can see this is the thickness of I think I showed you before, yeah, the thickness of the flow here. You can see that the membrane is always the light line, as you can see here, okay? And you see clearly here the fouling deposition on the top of the spacer, while in the whole pillar spacer, the membrane is quite clean, okay? So we use this for 0.5 bars, and this is for 1 bar. As I told you, the 1 bar enhancement was less because we still find some deposition on the membrane surface, but it's much less than a commercial spacer, as you can see here. That reflects to the enhancement of 65% compared to 75% with 0.5 bar. So in general, in UF, we use less pressure, not only for energy, but also for less fouling propensity. So we have shown that with OCT help that that point is valid. So the shear stress distribution, as you can see here, again, commercial, then you have pillar and hole pillar. So you can see that the commercial spacer has a symmetric stress distribution. Here you can see with the highest shear stress under the filaments. So here, because as I told you, in the pillar, the filaments is like in the middle of the pillar. So we have flow underneath or beneath the filament. While the pillar and even the whole pillar and even the pillar, they have symmetric stress distribution here and lower shear stress value. So when the spacer is attaching to the membrane, you have more shear stress because of the flow is like jumping, which is good for hydrodynamics, but very bad for fouling deposition, as we have explained before. So the one in the middle, that's why the pillar spacer had higher performance because we have lower shear stress and, of course, enough shear stress to remove the foulants, but not too much to promote biofouling deposition, as you can see here clearly in this distribution. So in summary of my presentation, so we just showed that commercial spacers design are really good, but do not trigger the unsteadiness at a typical operation conditions. That's why we found a lot of fouling. Independent of the applied pressure, the whole pillar spacer was always the highest, given the highest performance. It was found that it has the lowest initial channel pressure drop because we have these holes and we have void underneath the filaments. It was also, it produces a symmetric velocity profile that is roughly the same average velocity magnitudes as I showed in the last slide. And this spacers produce high flow velocity by forming microjets at the exit of these holes that eliminate the dead zones inside the spacer cells. And I also showed that increasing the applied pressure results on higher biofouling compared to lower pressure, which has been also reported earlier. Thank you very much for your attention. That's all.
Thank you very much, Professor Ghaffour, for this very enlightening presentation on feed spacers. Are there any questions from the panel or the participants? Because I don't see any questions in the panel.
There is one on the chat.
Okay.
You mentioned the increased porosity in case of perforated spacer, but it doesn't. But it is not the final performance decided by the porosity of the membrane, regardless what porosity. Yes, I agree. The porosity is just an added value because the flow is obstructed by these spaces. So if you open more, then your flow is running and you have less pressure drop. But it's not the critical point, of course. Yeah, I agree with you. But it's helping. So we have less pressure drop under the same conditions as I showed in parallel. When you have holes instead of solid space.
And then
Others,
there's one question.
There's another one?
Yes, there's one in the chat. If we talk cost benefit, how are these 3D printed spacers compared to commercial ones?
In my opinion, of course, when we did in the lab, we have to buy our own 3D printing. And so now, of course, most of these spacers are patented, and we have a fund now, transitional fund given by KAUST to commercialize these spacers. And we are in contact with spacer manufacturers. They have big machines. Then they have just to change the CAD, the designs, and then they just produce the spacers. I'm not sure if they are more expensive than the commercial spacers. They use the same material. We use the same material used in the commercial spacer. And maybe, I don't know, I would say I don't think there could be an additional cost because we are using the same materials, and maybe less polymers because they have holes. Maybe more time in printing, I don't know. But there is nothing to show that there is an increase in the cost. I don't see that, but we will have more clear answer maybe in the near future.
Then I have two more questions. One question is regarding the material for the hollow pillar spacers.
Same materials. So we bought polymers from. There are a lot, but we choose. I don't have in mind. I can see in the paper, but. We choose those used by the spacers manufacturers, especially one in the US. And anyhow, we use different also polymers. But as I said, we produce ourselves everything, including the commercial spacer. We produce it ourselves, just to have, because the thickness is also important on the spacer, just to have the same spacer. So we use the same material everywhere.
Okay, and then we have one other question. It's about, we know that there are studies on development of corrugated patterned membranes. For example, spacers are printed directly on the surface of the membrane and become therefore an inherent part of the membrane. This way, we get the benefits of higher porosity, higher flux, and turbulence promotion without addition of any foreign additional materials to the membrane. What are your thoughts on this?
So I'm following this works, of course, and actually one of my very good friends, colleagues from Khalifa University in UAE, they proposed this. Actually, these spacers were also proposed earlier, but now is with more advanced technology. I fully agree that these techniques are good, really good in terms of turbulence promotion. But the problem may be, I think, for scale up, I don't know how these two corrugated membranes will be in spiral wound. They do really not need a spacer to have space between them. This is one. The second, these corrugated are also more complicated than feed spacer. They have some caves which might have some turbulence at the membrane surface, because with this way we have more membrane surface area, to be honest with you, because we have more. But they might have some voids which create maybe some dead zones, or maybe foulants deposition would be. So I fully agree that this is also a very good technique, and we just go in parallel together, and we see hopefully both of them will be giving very good results and be implemented in. So why we didn't touch the membrane? First, I'm not a membrane maker, but second, our intention is to scale up. So we just use what is the state of the art. The RO technology now is the most successful membrane. They use a spacer, I am using spacers because I want to compare really in the real life. The corrugated ones are more maybe advanced because you are touching the membrane, and we should have the integrity of the membrane and a lot of work. So I'm following this from a lot of teams actually working on that.
Maybe one final short answer to the final question. If the packing density of the spacer increases, can it further promote the turbulence and improve anti-fouling capacity?
Packing density? You mean the thickness or?
Yeah, for example, a thinner diameter and a smaller grid size.
Yeah, so of course, we did a lot of comparison with different diameters. The big, higher diameter is good for us actually, but technically and maybe footprint and so it's not favorable in commercialization. I mean, we also contacted the membrane manufacturers. They want to reduce actually the thickness of the spacer instead of increasing it, while we know that thicker is better because you have more turbulence. But the pressure drop also was one critical point. But for the non-hole, for the hole spacer, perforation is good because we can put holes, and so I just suggest to see the papers. I put some references in this presentation, but I would be happy to share the results of the different thicknesses of the spacers we have used.
Great. Then thank you very much for this excellent presentation. I would like to give you a small applause, but